All right, folks, sorry about that, I'm late. All right, so we left off talking about gases. Oh, I should let you know, I can see your midterm 3 scores, and you did fairly well, so good job. But we aren't releasing those grades yet. We have a little bit of a dispute over one of the questions. So the question is whether to just give everyone credit for that one question or not. So you will get your results back soon. The grades will be posted, but you won't get your actual responses for a while because we have to wait until all students take it. We will get them before the final, so definitely that. All right, so we left off talking about gases, and so I mentioned we always have pressure around us, all right? Our atmospheric pressure, that's where we live and breathe. All the gases that we're breathing is coming from atmospheric pressure. So we made some comparisons between different conversions between different pressure measurements, ATM being the most common, but oftentimes we see millimeters of mercury, which is also the same as a torr. We talked about Pascal, which is the SI unit for pressure, and you see all those conversions there. But one that we oftentimes see, at least here in America, is pounds per square inch. So for example, if you fill up your car tires, do you know what pressure your car tires should be at? About 30, yeah. Depends on how big your vehicle is. My big SUV only takes 30 PSI, but my little car takes 32. But if you want to feel it, this is what 14 PSI, 14.7 pounds per square inch feels like. So this is the pressure on our bodies all the time, because one atmosphere is 14.7 PSI. Does anyone want to feel it? Want to feel it? I'm going to put it on your toe. Do you? Yeah, because you'll definitely feel it, right? It's a lot of weight. It's 15 pounds per square inch. Isn't that a lot? Yeah, it's like really, does anyone want to like feel it? It's like freaking heavy, all right? And this is on us like all the time, all right? So like you can like hold it. This bar is really heavy, all right? I'll put it up here if you want to feel it after class. But, you know, we as humans evolved to have, you know, this pressure around us all the time. So if you were to go to outer space where there is no pressure, you would probably, if you didn't freeze immediately, you would probably explode if that was the case. So I have a lot of demos I want to do today because gases are cool. Gases are cool. All right, so that's our PSI stuff. So it's lots of pressure coming from our atmosphere, and it's a lot of pressure that can help us do a lot of different things, and I'll kind of show you the power of what that pressure can do. Maybe I'll just show it right now. I'll just show it right now. So this bar is really heavy, and to kind of prove it to you of how much pressure that is, I have a soda can here, all right? I call it soda, all right? So this soda can right now is empty, but when I say it's empty, is it actually empty? No, because what's in it? What specific gas? Air. Air is in it. So it's not necessarily empty. I mean, it's empty because it no longer has soda in it, but you know. All right, so let me put my goggles on. So what I'm going to do is start this Bunsen burner. I have a little bit of water on the bottom of this soda can. Come on. Come on. No. Oh, there it goes. There we go. All right, so I have a little bit of water on the bottom of this soda can, and so what I'm going to do is just quickly boil the water that's in there. And what that does, we said that there's air, oxygen, nitrogen gas inside the soda can typically when it's empty, but when I boil the water that's in this can, all that water vapor, H2O gas, is going to replace the nitrogen, oxygen gas that's typically in there when we think about it being empty. All right, you got that with me? So what I'm doing is boiling water. So on the inside of the can, we'll have H2O gas. Is it boiling? So this Bunsen burner is like scaring me. Boil. I probably should, yeah. I know, they didn't give one to me. All right, come on, boil. All right, so, is it boiling? I'm like burning the can. Okay, hopefully this works. All right, I'm just gonna do it. All right, and so what I'm going to do is slowly, oh no, it's not working. This is what happens when I come late. And sorry about this, guys. We might have to try it again. All right, so anyway, what's going to happen, hopefully, is the water in the can boils, replacing the air, the oxygen, the nitrogen gas with water vapor. So when I flip the can over to put it in this like cold water bath, what will happen is that water vapor will condense immediately, right? The water vapor will condense, so it'll go from a gas to a liquid. So then there'll be no more gas inside the can. Right, and then if you kind of think about what happens next is that since there's no more gas in the can, there's no pressure. But think about on the outside, our atmospheric pressure, that's still there. Are you boiling? I asked her how long it would take, and she said just a little bit. Oh, I think it's doing it. Okay, there we go. There we go. Is it doing it? Okay, I hear it boiling. Okay. Oh, there it goes. There it goes. All right, so, all right. Sorry, that didn't work as, also these tongs are really bad. I can't even pick it up. All right, so there's the pop can, all right? There's the Ohio in me showing. So there's the soda can. So what happened was water vapor filled up the can. When I put it into this cold water bath, that water gas immediately turned back into a liquid. But remember, it displaced, all that water vapor displaced the air that was in the can. And so there was no more gas inside the can once that water condensed. And yes, it got squished because we still have atmospheric pressure around us, 14.7 psi all the time, and essentially all the gas particles in our air that we breathe, it was enough force to squash our aluminum can. So there we go. It took a while, but I did it. There we go. And I didn't even practice. Okay, so 14.7 psi, right there. Right there. So all of that pressure right there on our Earth all the time. And so we have ways to measure it. We can use a barometer to measure it. And so this whole idea, we're going into our named gas laws now, looking at how our pressure, volume, temperature, how are all of those related, is all based upon this fact that gases are constantly trying to equilibrate themselves with the surroundings. So when that pop can squished, it reduced its volume because there was so much extra pressure on the outside and there was no pressure on the inside. And so that's kind of demonstrating that there are gases here changing their volume in order to equilibrate themselves with the forces outside of that sample. We talked about manometers and how the gas sample versus atmospheric pressure, how it has to balance out. I think someone gave a great analogy when we were talking about this, when there's extra pressure coming from the manometer, from the actual height difference of the manometer. It's like an arm wrestling type of thing. So all the pressure on this side equals the pressure being exerted here. So in this case, the external pressure is greater than that of the gas because that gas needs a little bit of extra help to get that to be equal. Or on this example where the gas is actually exerting more pressure than the external pressure because there's a little bit of extra millimeters of mercury up on the other side. So the gas is kind of winning out in that scenario. So we can tell a little bit about the pressure of our gas sample based upon the height of the manometer. And so a manometer is different than a barometer. Barometers just measure atmospheric pressure. Manometers can measure actual gas samples. Okay, and then we talked about getting into our named gas laws. So we're going to be relating pressure, volume, and temperature in our named gas laws. And another thing that we'll be talking about in relationship to gases is moles of our gas, because that tells us essentially how much sample we're working with, the amount of moles of gas we have, but it's also directly proportional to volume of your sample that we have. So these are the common units that you'll see, so definitely know how to convert between all of these. That's assumed. I assume you know how to do those already. And oftentimes we'll talk about STP, temperature and pressure, just because it's easier to write that than to write 0 degree Celsius and 1 atmosphere. It's easier to just write 3 letters to mean that same thing. All right, so our named gas laws. Let's do them and do some more demos. So our first one here is Boyle's law. So essentially, laws are written in sciences when we see observations over and over and over and over. Once we see the same observation over and over, typically a law is written in which we can relate two phenomena or two properties to one another, such as like the law of gravity, that like if I drop an object, it will fall down, and that whole idea that a larger body will always attract a smaller body, because it happens over and over and over. Anytime you drop something on Earth, it will always fall, right? That's a law. Like it never doesn't happen. So that's why we call it a law. And so this is a law named after Boyle that says, okay, at a constant temperature, pressure and volume of a sample, of a gas sample, are inversely proportional to one another. So the big idea with these laws that we're going to talk about, so there's like 3 or 4 different ones, the sample, we're looking at one sample and thinking about how it changes its properties. So when we have a sample and we like change its temperature, and then something happens, the amount of sample we have does not change. So the big idea here is that the amount of moles of our sample does not change with all of these laws. This is different from when we use the ideal gas law, which is coming up in a few minutes. So Boyle's law: at constant temperature, volume of a gas and its pressure are inversely proportional. So this is the demo I have for Boyle's law. Okay, meaning if they're inversely proportional, if I increase the pressure of a sample, how would you expect the volume to change? Would it go smaller? Yes, it would go down. It would get smaller. If we would lower the pressure around a sample, the volume is predicted to go up in that case. And really, this whole idea is because the gas sample is trying to equalize the forces on the inside of your container and the outside of your container. So I have this marshmallow man. All right. Does anyone know how to make a marshmallow, like from scratch? No? No. Okay. I watch a lot of Food Network. So what you do is you take molten sugar, you put it in a stand mixer, and then can you just imagine what you do next? You turn the stand mixer on, and when you turn the stand mixer on, it mixes it, but the whole action of mixing it does what to the molten sugar? It puts air into it, right? Because we know marshmallows as these nice, white, fluffy things. So when you make a marshmallow from scratch, you put the molten sugar in a stand mixer and you whip the crap out of it. So you put little air pockets inside the sugar. And then the sugar hardens, and then you have a marshmallow. And there's gelatin in there and stuff too to make it squishy. But each of those air pockets is filled with air, which is a gas. So these marshmallows represent tiny little air pockets filled with a certain volume of gas. So I have a vacuum pump here. Vacuum pumps evacuate the pressure inside this bell jar. So right now, when I have the bell jar open, this marshmallow man has what pressure pushing on it right now? 1 atm, 14 pounds per square inch. But when I turn on this vacuum pump, what it will do is reduce the pressure on just that marshmallow man. All right, so let's just do it. So what do we predict will happen? He will get bigger, yes. And you're right, he will get bigger. But then something else will happen as well once I let the pressure go. Crap. How do I turn it on? Okay. There we go. All right. Okay, so Marshmallow Man, let's watch him. And you make sure that there's a good seal. Okay, do we see him? Do we see he's moving? He's moving? Come on, go. Go. See he's getting bigger? Slightly? Yeah? Yes, you see it? He's getting bigger. Yes, and that's because we're reducing the pressure inside that bell jar. And then so what I'm going to do is quickly take off this tube so the pressure goes back to normal. And think about what may happen when I make the pressure go back to normal. All right, so there we go. All All right, so when I when I pulled off this tube, all of the air pressure returned back to the bell jar. And what happened is because the volume got so big of the marshmallow, it kind of broke all of those little air pockets that we delicately, tried so hard to whip into the marshmallow. And so when we brought pressure back in, it just collapsed all of those bubbles. So if you ate this marshmallow, it would be really dense because there's no bubbles inside of it. And it'd be really gross. It'd just be like really sugary mass there. All right, okay, so Boyle's law, volume pressure inversely proportional to one another, but oftentimes what we use is this equation that says, hey, the product of the pressure and volume in one condition equals the product of the pressure and volume in your second condition. So if your P2, let's say, is greater than P1, so if pressure increases, we already predicted volume has to go down. And so you can kind of see how, since they're a product, that we maintain that relationship within Boyle's law, that they're inversely proportional. So this is basically saying the same thing, that if P goes up, V goes down in order for these two sides of the equation to remain equal. And so the whole idea with these named gas laws is that we need the units to be the same on each, like the pressure units need to be the same on each side, the volume units need to be the same on each side when we use it. All right, and we'll do some examples. All right, so our next demo here is Charles' law relating volume and temperature. Volume and temperature. Oh, I should point out, actually, with Boyle's law, we see that temperature is not in Boyle's law. We see that temperature is not in there. And the whole idea, because temperature is not in here, we don't need to kind of think about temperature when looking at Boyle's law relationships, because temperature remains the same. And that's part of Boyle's law, at a constant temperature. So it stays the same during the process. So for example, when we were doing that demo with Marshmallow Man, the temperature of the marshmallow before I did it was room temperature. The temperature of the marshmallow after he was nice and big was still room temperature. So the temperature of Marshmallow Man did not change at all. So that's important when thinking about Boyle's law. So kind of on that same vein with Charles' law, here it says at a fixed pressure, volume and its temperature are directly proportional to one another. So as the temperature of an object increases, typically its volume increases. As the temperature decreases, volume decreases, but at a constant pressure. But thankfully for us, we live on Earth where the pressure is pretty much constant all the time. All right, so there's always one atmosphere on us. So the demo I have to show here is a demo with liquid nitrogen. Liquid nitrogen is really cold. It's negative 77, or no, I think it's 77 Kelvin is its boiling point temperature. So this is like the same nitrogen you and I breathe, but it's just in the liquid form. It's really cold. See, it's really cold. So the smoke you're seeing is it's water vapor. All right, so it's really cold. All right, let's think about this balloon. So I have this balloon here. It's at a certain temperature. What's the temperature of this gas sample I have? Room temperature. So if I dip this balloon into liquid nitrogen, which is really, really cold, its temperature will go down, right? It'll go down. So if its temperature goes down, what do we think will happen to the volume of the balloon? It'll have less volume. It will shrivel up. Yes, so let's do this. Is this the one I'm supposed to use? Okay, I have to do it in here. Okay, I have to do it slowly. All right. So there it goes. It gets smaller. See it? See it? Okay, so the balloon's really cold. It got smaller, but what if I warm it back up? Like if I warm it back up, what will happen? Well, it's already doing it. It goes back. So once I warm it back up to room temperature, its volume will go back. All right, and that's demonstrating Charles' law. All right, when we show this demo to kindergartners, they are amazed by it because they think this is what kindergartners think and I guess regular non-science people that, yeah, okay, I get it cold, it gets small, but when people think, oh, when samples get small, that the gas like disappeared or something, right? You would think that. You can see how like someone who wasn't into science would think that there's no gas in here. because it got so small, but that's not true. There's still the same amount of gas. If we weighed the balloon, it would still be the same weight. There's still the same number of particles within there, but just because we cool it down or warm it up doesn't mean that the number of moles of sample changes. So you could do this like an infinite number of times until the balloon broke, or something like that. So there you go. Yeah, children and adults love this demo. Okay, so there we go. All right, there are the demos. So that was Charles' law. Volume, temperature, directly proportional to one another. So the equation we typically write is this way, where volume and temperature are over one another. So you can see if, like temperature goes up, like T2 is larger than T1, then volume also has to go up in order for that proportion to be equal to one another. The trick is here, and I mentioned it before, whenever we do calculations with temperature regarding gases, temperature needs to be in the unit of Kelvin. All right, yes, Kelvin. And so the fun thing about Charles' law is this is where the whole idea of absolute zero came from. All right, so the idea of absolute zero is literally the temperature, the lowest possible temperature you can possibly have. So kind of theoretically where this number comes from is if we take a gas sample and we cool it down so much that the volume becomes zero, the volume is zero, at that temperature, we see, like, for a whole bunch of different temperatures, or a whole bunch of different samples, they all converge at one place. They all converge at negative 273 Celsius, is the temperature that all gas samples will essentially have a zero volume, where all of those gases condense into those gases condense into like the liquid or solid phase within there. So the idea that all samples will converge at one temperature, that is absolute zero, that happens at negative 273 Celsius, which we call 0 Kelvin, right? So that's just like a little side thing. All right, and so the last, second to last gas law here is Gay-Lussac's law, but really Gay-Lussac's law is the same as Charles' law. But I'll show it to you anyway, that pressure and temperature are proportional to one another. So as pressure goes up at a constant temperature, at a constant volume, that as temperature goes up at a constant volume, pressure will go up for that sample. And really it's just it's similar to our Charles law that we talked about previously. I don't have a demo for it because oftentimes trying to show this demo, you make things explode. But there's like a Simpsons episode that I like to think about because I think we can use our intuition a little bit here, thinking about how pressure and temperature are proportional to one another. I think Apu here was coming to Homer for like family advice, like child advice, and Homer was cooking dinner on the grill, and he put cans of beans on the grill, but he kept them closed. All right, so he put them like straight on the fire, but he kept the cans closed. And Apu, basically, he could anticipate, like, hey, if you leave those cans of beans on the flame, they're going to explode. Right, and really what they were doing was exercising Gay-Lussac's law, that as temperature increases, pressure inside the can will increase to a certain point, though. Like the can only accept a certain amount of pressure, then it will explode, and that's essentially what happens. Apu gets his shield out to protect himself because he knows it's going to explode because temperature and pressure are proportional to one another. So that's my demo, I guess. There. If we put it together in an equation, it's very similar where pressure, temperature, they're over one another. And so the whole idea, P1, T1, that's your pressure and temperature at state 1, P2, T2 at state 2. The whole idea is that the sample is staying the same. It remains the same. The number of moles of sample remains the same. You're only changing pressure or temperature in this example. So I showed you a bunch of equations. Okay, and the whole idea is like, okay, sometimes two things are related to one another, but one thing has to remain constant. As you know, I'm lazy and I hate to memorize anything. So we can actually put together all of those named gas laws into one equation. Okay, would you rather memorize 3 or memorize 1? 1, all right? And so the combined gas law actually has all of the components of the named gas laws. I'll just show you the trick on how to use it. All right, so the combined gas law puts together all of those that we just talked about, where we get an equation P1 times V1 over T1 equals P2 V2 over T2. And so the trick is here, is if any one of those variables stay constant, so let's say volume of your sample remains constant, then you can just drop it out of the equation. I mean, you can put it in there, right? If the volume of your sample is like 5 liters, V1, but it doesn't change, so that means V2 is 5 liters. Don't you see mathematically how they both cancel on each side if it's the same number, right? So if you have any variable that stays constant, it drops out of the equation and you get that specific named gas law. So that's why you can just memorize 1. I just memorize this one and do a bit of reading comprehension in the question to see, okay, what variable is remaining the same. In some questions, all of the values may change, and there might be nothing that changes, remains constant, but that's okay too. We can still calculate it as long as there's one variable left. All right, so let's do some calculations. All right, and with these gas law problems, yeah, it's a lot about reading comprehension, okay? Identifying, okay, what's P1, what's P2, how's it changing, etc. So I always like to label things, all right, when reading it. So here, at a constant pressure of 1.6 atm, we have a sample of CH4, and it occupies this volume at this temperature. What volume will it occupy at this new temperature? So a couple things we can do. I just go through the question and see and look at the units of things. So 8.32 liters, to me that sounds like a volume. I'm going to call this V1. All right, so looking on in that sentence, 350 Kelvin, that sounds like a temperature, and it's related to that first volume we talked about. So this is T1. All right, so V1 and T1 are connected. They're related to one another. That's the sample at condition 1. All right, oh, and so the one value I kind of skipped over was at constant pressure. To me, this sounds like a pressure value. We can call it P1, but because it remains constant, P1 is also equal to P2. So in this case, when we use the combined gas law, that pressure unit just falls out of the equation. We don't actually have to use it. So reading on, it's saying what is the volume of the sample at this new temperature. So to me, that 420 Kelvin sounds like T2, and we're solving for V2 in this case. So putting together the combined gas law, P1 V1 over T1 equals P2 V2 over T2. Since pressure remains constant, the pressure term, we can just cancel that out. I mean, you can put the 1.6 on each side, but mathematically it cancels out. And so at that point, we have all the values we need. We're just solving for V2 in this case. Luckily for you, in this question, all the units match, so we don't have to convert anything. But do know if those temperatures were given in Celsius, you would have to convert them to Kelvin before we do this. So I just put in all the values, just, yeah, as is. So V1 is 8.32 liters, T1 is 350 Kelvin, equals V2, that's what we're calculating, over 420 Kelvin. All right, and then you just solve for V2. All right, so see how all the units match. So what is the unit that V2 will be in when we calculate this? If they have to match. It'll be in liters, all right? So yeah, V2 will be in liters. I get a actually, even before we do this, which law is this? Which law is it? The one that relates volume and temperature with one another? Charles, yeah, if you look up here, which one was volume and temperature? Was this one, the balloon one, the liquid nitrogen one? That was Charles' law. Charles' law says volume and temperature are proportional to one another. So in this example, temperature is going in what direction? Up. So volume should go up as well. So when we calculate V2, what do we get? What do we get? Did anyone plug it into their calculator, or are you just going to let me do it? 9.9 something. How many sig figs do you think we should have? Probably 2. I'm just going to, or 3. I'm going to say 3 sig figs here. So volume is 9.98 liters. Yeah, so does that agree with Charles' law? Yes, so that's the way to check yourself, all right? Just to make sure that, you know, those laws work out. Okay, so this next one. So we have a sample of gas that occupies 2 liters. So I'm going to call that V1. At this pressure, I'm going to call that P1. And 0 degrees Celsius. So that is T1. I'm just going to rewrite that into Kelvin right now. So that's 273 Kelvin. Yeah? Yes. Since it's in Celsius. So now it asks what temperature in Celsius. So to me, that sounds like it wants us to calculate T2. When the gas displays a pressure of 10 atm, so that's P2, and is in a tank of 5 liters, so that's V2. And now let's just plug and chug and make sure that all of the units match in this case. So within this question, can we cancel out any of these PVT terms? No, because everything changes. Everything changes. We are calculating for T2 in this example. And so I'm just going to plug everything in. So P1 is 8.60 atm. V1 is 2 liters. T1 is 273 Kelvin equals 10 atm. V2 is 5 liters, and we're solving for T2. So when we solve for T2, what unit will that be in? Kelvin. When it comes out of this equation, it's in Kelvin, so we just have to do a little bit of arithmetic to get it into Celsius here. So I get that T2 is 793.6 Kelvin. Since the beginning temperature has 3 sig figs, I'm going to round to the ones place for our Celsius temperature as well. So I get a Celsius temperature of 520 degrees Celsius. Is that what other people got? I hope that's what other people got. Okay. So with combined gas law, lots of just reading comprehension. Can you identify how your system is changing and identify your condition 1 from condition 2? If you look at the overview sheet for chapter 10, I just posted the key. There's tons of practice. I wrote so many of them. All right. So, all right. So those are our combined gas laws, the named gas laws. The kind of overarching picture with those named gas laws is that the sample, the amount of sample we have does not change. That we're just changing the environment of that sample. So thinking about if we look at the sample, the number of particles inside the sample remains the same in your different states. So now we're bringing this new component that we discussed regarding gases, and that's the amount of gas you have, moles of gas. All right, so Avogadro's law says that the more moles of gas, the more sample you have, the larger its volume will be. All right, and so using this law, we can kind of relate all of those other named gas laws to give us our ideal gas law equation. So this equation, the next one, oh, I didn't write it here yet. This is kind of mathematically how we get to it. So I'm just adding Avogadro's law to our combined gas law here, all right, where now I can say that the volume is proportional to the number of particles I have times the temperature over pressure, or sorry, not equal to, but proportional to. That the volume of your sample will increase if your amount of sample or the temperature increases, or if the pressure decreases. That's what this proportionality is saying. So basically this means is that if we kind of move everything to the side, we can say that N times T over pressure times volume equals some constant. If I just move this volume to the other side, I can say all of these terms equal some constant, right? So that constant has a special name. It's called the gas law constant, all right? And this is our, we call in the science community R, the gas law constant. R has a lot of different units. has a lot of different masks that it can wear, but within gases we use one specific kind. But there are some other R values that we use out there. So be very cognizant of what unit of R you want to use. So putting that all together, this is where we put that constant, where we say that N times T over P times V equals a constant. We can rearrange it into the ideal gas law equation, which I call PIV-NERT. All right, pressure times volume equals N, which is the number of moles of gas, times R times temperature of your sample. And so how this equation is different, and in your mind, what I want you to think about when to use this equation versus the named gas laws. Named gas laws, when you have one sample and you're just changing its conditions. We use the ideal gas law when we are talking about one specific sample, not changing conditions. You know, when we want to know some type of property of one specific sample with a certain number of moles of gas. All right, so the idea is here with the ideal gas law, this is the easiest way to use it. Make sure whenever you put a pressure value into this equation, it's an ATM. Volume always should be in liters. N is always in moles. Temperature is always in Kelvin. If you do that, if you make sure, because it's easier to convert those things into ATM, liters, moles, or Kelvin, because we already know those equalities. If you do that, then you only have to memorize one value of R. Because I told you that R has a lot of different units to it, different values to it, but if you just memorize one of them, which is 0.8206 liter ATM mole Kelvin. If you just memorize that one, it's way easier to just convert pressure, volume, temperature to the units we need than to memorize like 8 different forms of R. Does that make sense? So this is the R to memorize. There's also one other one. There's basically 2. If you're in the sciences, there's like 2 important ones that you use. All right. I'll leave it at that. Okay, so, and in the unit of R, you see what units of P, V, T that you need. All right, so when you are given a pressure, volume, and temperature of a sample, you can calculate N. This is essentially what that means. If you don't know one of these variables, but are given 3 other ones, you can calculate that missing piece there. All right, so now that we're talking about specific samples of gas at specific temperatures or pressure or whatever, we can look at different gas samples and see how they're related to one another. So let's pretend we put 1 mole's worth of gas into 3 different containers. So one of the gases, let's say, is helium, the other one is diatomic nitrogen, and then the other one is methane. So if I say 1 mole of gas, that means N in our equation is 1 mole. And let's say each of those balloons, those containers, are at STP. So recall what STP means. It means 1 ATM and 0 degrees Celsius, or temperature is 273 Kelvin. So I know the pressure, I know the temperature, I know N, so I can calculate V, the volume of that sample of gas. So since N is 1 mole, I can just rearrange these things. 1 mole times R, our gas law constant, 0.08206 liter ATM mole Kelvin. Let me move stuff around. There we go. Volume equals that times temperature times 273 Kelvin. Over pressure, which I just said was 1 ATM. If you stick that into your calculator, what you get is that 1 mole's worth of gas has a volume of 22.4 liters. There might be more sig figs there, all right? So 1 mole of gas at 1 ATM and 0 degrees Celsius will occupy a volume of 22.4 liters of volume here. So if we think about all of these balloons that we have, each of them are at 0 degrees. Each of them have a pressure of 1 ATM. So shouldn't all of them have a volume of 22.4 liters? All of them. That's what this is saying, that it doesn't matter what the identity of the gas is, that the volume of a gas sample is only dependent on the number of particles that are inside that sample. Because within our gas law equation, N, the number of moles of gas, is the important factor that relates to pressure, volume, and temperature in that case. So even though these are all different gases, like have different identities, they all have the same exact volume. And that's what you see kind of up here on this graph, that what we're calculating, that calculation we just did, is the ideal volume of 1 mole's worth of gas. So this is the volume measurement we get for an ideal gas using PivNert. These are the actual volume measurements of 1 mole's worth of all of these gases, and see how most of them are really, really close to the ideal 22.4. Some of them deviate a little bit. You see that? So like nitrogen, helium, hydrogen, see how all of these like are basically spot on the ideal, that ideal volume. You see that? But then these 3 deviate a little bit, right? But still pretty close, right? At the end of the chapter, we will talk about the details of those deviations, because we go into it in an insane amount of detail in this class. All right, but for now, let's just think about the ideal gas law within here, that all gases will, if you have the same number of mole, no matter the identity, will occupy the same volume, as long as it's at the same pressure and temperature. So we just said that those 3 balloons have the same volume, but we said they have different identities. So what property does differ between them? The what? Their identity is different. So if I have 1 mole of gas in all of them, so 1 mole of helium, 1 mole of hydrogen, methane, 1 mole of nitrogen, if we look at these values, what is different? If we look at like those rows of values, the mass, right? Because their identities are different. Since each balloon contains 1 mole of gas, and they're all different identities, they actually have different masses there. So, you know, I was showing you like the magic here that the volumes are the same of gases when N is the same, but the masses, the densities are different. The volumes are the same, the masses will be different, so therefore the densities will be different. So yeah, the big difference that I want you to see in this line, how the balloons are different, are the masses of the gas. So let's see, can't we rank these gases in terms of their density? We shouldn't have to calculate anything, because as long as we know that density equals mass over volume, we know that all of these balloons have the same what? Volume. So we should be able to rank these based upon density without doing any calculations. Which balloon will be the densest? The nitrogen, right? The heaviest one. Whichever balloon is the heaviest one will be the densest. So N2 will be the densest. Okay. Then it will be which one? CH4, and then it will be helium. I mean, you can calculate it as well, but you shouldn't have to. Right? And the whole idea here is that all of them have the same volume. All the balloons have the same volume, just the masses are different. So the heaviest one will be the densest. Okay, so let's use the ideal gas law in calculations. Okay, so these are typical ones that we give on exams. We don't typically just give you the numbers straight out. We make you do a little bit of manipulation, because we've talked about moles before, moles of gas or moles of substances previously. I don't have to just give you the number of moles of a sample. I can give you instead grams of that sample and require you to calculate moles using molar mass. So going through this equation or this question, so we have 12 grams of helium and we place it in a rigid 5-liter gas cylinder. So 5 liters is what variable? Volume. I always like to go through and label my things. I'm a labeler. Okay, so this container will explode if the pressure inside exceeds 200 atm. So that variable, that measurement sounds like pressure. Yes. So at what temperature in Celsius will the cylinder explode? So here we're using PivNert, not our combined gas law equation. So just going through all the things that were given, they give us pressure, volume, temperature, but wait, no, they don't. They don't give us temperature. That's what we want to find out. So the one thing we don't know, R is always a constant, so you know that. We don't know N, the number of moles of gas we have. But there's one piece of information I didn't use yet. That was the mass that was given at the beginning. So I can't put 12 into our PIV-NERT equation because the unit's in grams. So I need to convert that gram amount of helium to moles first before I can put that into our PIV-NERT equation. So we see that, all right? So I make you do a little bit of work before you can plug it in. So let's do that. So we have 12.00 grams of helium. We want to convert that to moles. Helium has a molar mass of 4.003 grams per 1 mole. And so whatever this is will give me my N value. So this is 2.9977 moles of helium. So this is N. That's what I'm going to plug into my PIV-NERT equation and calculate for T. So putting everything together, 20 ATM, volume is 5 liters, equals that N value I just got, so it's basically 3 moles. R, which is a constant, so I don't know if you're given R at this point. I would just memorize it. So 0.08206 liter ATM mole Kelvin, and then T. So that's what we're calculating for, temperature in this case, because it's asking at what temperature will we explode? Okay, and so temperature in this case, if you do the math there, is 406.5 Kelvin, but it's asking for it in Celsius. So then convert that to Celsius, it is 133 degrees Celsius. All right, so if you put that helium gas cylinder into a campfire, it will probably explode. Good? Yes. All right, so my strategy here for PIV-NERT equations, just go through the question, identify those different units, figure out what you still need, and plug those things in to calculate our PIV-NERT equation. All right, so the second question, calculate the number of molecules in a deep breath of air, which has this volume at body temperature, so I give you the temperature at this pressure. So I want you to calculate the number of molecules. So if we calculate the number of moles first of gas, we can calculate the number of molecules. How are moles and molecules related to one another? Avogadro's number, yeah, the 6.022 times 10 to the 23. Right, so if I have 1 mole of gas, that's actually 6 times 10 to the 23 molecules of gas. So to me, this just sounds, oh, okay, plug this into our PIV-NERT equation, solve for N, and then convert that to molecules. All right, so let's plug all that in. So 735 torr. Can I just leave it like that? No, you got to turn that into ATM first. So over 760 torr. That will give it to me in ATM. Times volume, 2.25 liters. That's how, I guess, large your lungs are. Equals N, so that's what we're calculating, the number of moles of gas in one deep breath. R, I'm just going to put R, because you know what R is. And then temperature, so 37 plus 273, which is 310 Kelvin. All right, so then just solve for N in this case. So N is 0.08554 moles of gas. All right, but that's not my answer. This should probably have 3 sig figs, but I'm not done yet, so I never like to round early. So then we just take that answer and convert it to molecules. So 1 mole of any gas is 6.022 times 10 to the 23 molecules. And so what you get is 5.15 times 10 to the 22 molecules of gas are in 1 breath of air. So hopefully you got that. All right, so this question, not too different than the one previously. This is how we can kind of go above and beyond just the PIV-NERT equation, that we can go make you do a little bit of extra calculations there based upon things you already know from previous chapters, because you guys are really smart, so you can do it. All right, so On to applications of the ideal gas law. So the whole idea, PIV-NERT here, we can calculate moles of gas. Thinking back to other chapters where we talked about moles of substances, we can connect this to the idea of stoichiometry. All right, now we can calculate the number of moles of gas consumed or produced in a chemical reaction. And instead of, calculating grams of that product, that's what we used to do in chapter 3, remember? Now, instead, as long as we know the pressure and the temperature, we can figure out the volume of gas that's produced in a chemical reaction using PIV-NERT instead of, getting to grams using molar mass. Does that make sense? So putting that together in stoichiometry here, really this is no different than we did previously. So here I tell you, okay, if you start out with 200-ish grams of calcium carbonate, and we put it in a balloon and it decomposes and it fills up a balloon, what's that final volume? So recall here, we're making a gas, and so the only gas that's produced is CO2. And so remember what stoichiometry is. We're relating these coefficients. So for every 1 mole of calcium carbonate that reacts, how many moles of CO2 is produced? It's already balanced. So it's 1. So it's 1 to 1. So if we figure out how many moles of calcium carbonate decomposes, we can figure out how many moles of CO2 we get. But we're not done when we have n number of moles of gas. We have to plug that into our PIV-NERT equation. So kind of like writing the whole strategy here, really reminiscent of chapter 3. We are given grams of calcium carbonate. In order to use stoichiometry, what unit does that have to be in? Can we go to grams? Has to be in the unit of moles. So we need to go to moles of calcium carbonate. How do I go from grams to moles of calcium carbonate? Molar mass of calcium carbonate. All right. And I give it to you, so I'm very nice there. So once we have moles of calcium carbonate, we can use stoichiometry to get to moles of CO2. And that's a gas. So if we have other information such as pressure and temperature, which we do, we can get to liters of that gas as long as we have pressure and temperature. So we just plug it essentially into PIV-NERT, where that moles value is N in that case. So really the only new thing here is this last step. Everything up until here to here you've done before. Before we used to go to grams of CO2. But we don't measure gases in grams, we measure them in terms of their volume and pressure instead. So let's put that together. So I'm going to start with what's given, 272.55 grams of calcium carbonate. Use molar mass, so 100.09 grams is 1 mole of calcium carbonate. And then what do I do? I'm in the unit of calcium carbonate, so that's a reactant in this case. I want to get to moles of the gas that's formed, CO2. So 1 mole of calcium carbonate on the bottom, 1 mole up top. But if it wasn't, 1 to 1, if it was 1 to 2, then you would make sure you reflect those coefficients there. For whatever the reaction is. And then we're done with just moles of calcium, moles of CO2 in this case. So just kind of plugging in those numbers. This reaction, if all of that calcium carbonate decomposes, we will get 2.72 moles of CO2 produced. So that is N in our PIV-NERT equation. And then at that point, you just kind of plug everything in. Oh, but what's nice is they say that this balloon is filled at STP. So a little trick here, if you know that at STP, only at 1 STP, 1 mole equals 22.4 liters, you can just use that equality to get that. If we have 2.72 moles of CO2, this should also equal 61.0 liters using that equality, or you can just plug it into PIV-NERT, you'll get the same exact number. All right, but just save you a little bit of time. All right, so that's how much CO2 we would create in this reaction. So I think that's a good place to stop. We'll look at more applications of gases on Monday. More calculations. Oh yeah, so this is a very calculation-heavy chapter. So some of you might be happy. Have a good weekend, everyone.